Welcome, everybody. My name is Jaak Vilo. I'm organizing this summer school that we are running in here, Estonian Summer School in Computer and System Sciences. And within this summer school, we have one public event for everybody. I noticed about how to be a good PhD student. So I noticed at least a couple of professors now showing up, how to be a good, how to have a good, worthy PhD study period. That's good. I hope that there are some people who are now first time during this summer school in here, and it will be also video recorded. So that's why I'm doing this introduction again. So happy to have Christoph Lampert in here from Institute of Science and Technology, Vienna. Vienna was, yeah, Austria. He has been trained in mathematics, and his research topic is in machine learning and artificial intelligence image analysis. So running the research group in machine learning and computer vision. So we heard a lot about machine learning techniques that they are working on, but today the public session is about how to perform PhD studies in machine learning, but actually it's applicable to any field. So generically, how to build networks, how to, what are people doing during the PhD, etc. So without any further ado, I would like to hand over to Christoph, please.
Thank you. Thank you for the introduction. I'm happy to see some unfamiliar faces as well who came here. So this lecture grew out of an experience I made in the previous times that I talked at different institutions, at different summer schools, especially, that while the content of the lectures is typically science, the questions I got outside of the lecture hall were typically about a lot of other things, like how to apply to a grad school, what would it need to be accepted, what do you do all day, why are there so many papers that we can't read? So the scientific world consists not just of the actual science, but also of a lot of things around it. And since many of you are young researchers, probably at the beginning or considering a scientific career, I wanted to give this more general presentation about how to become a researcher, how to enter a good program where you learn a lot, become a great researcher, and what would it mean to take this career step later. So what do researchers do all day besides giving these kind of lectures? So as you already heard, I come to you from ISTA Austria. It's a research institute, publicly funded, and we are running a PhD program where people from all over the world come and can do a PhD degree, but we do not have undergraduates, which means we don't have local people that we can promote to PhD student, but we're completely searching worldwide, which means we get a lot of applications, and that means I read a lot of applications, and I know a little bit after 12 years now what makes a good and successful case and what doesn't. Okay, so first of all, I mean, being a scientist, trying to be a scientist is of course a very good idea. Science is everywhere. The world is dominated now with news that have some kind of scientific background. And in particular, when you think about what the world needs in order to advance and cope with the problems that we have, such as climate change and other things, then probably scientists are in higher demand than, I don't know, politicians. And when you go to any of the big events where scientists meet, such as computer science conferences in this case, you will see that there's a lot of demand for recruiting talented people into industry, into startups, also into academia. And I mean, people offer ridiculous salaries for for just somebody who has a bachelor's degree but knows how to, do scientific research of this type. It's definitely a possible choice to become a scientist and not starve on the street. For many of you, this might not be news, but let me just summarize anyway. So the career steps to become a scientist in academia are pretty much standardized worldwide. So first of all, you need to go to university, you need to study, and you obtain a bachelor's or master's degree, or often both. And then next, you can move on to obtain a PhD degree or any kind of doctorate. You will typically continue to stay in academia for a few years to be a postdoc, even though in computer science that's not necessary all the time anymore. Afterwards, if you're lucky and good, you can become an assistant professor somewhere and eventually be promoted to a professor with tenure, meaning that you now finally have a position that is not just a temporary limited contract. So by the time you become a tenured professor, you're typically in your 40s, and this is the first time you have a fixed position. Everything else before was temporary contracts of like a year or 3 years or 5 years or so. So it's a career choice that one has to think about if this is what you want. There's also a lot of science going on in industry, especially in computer science related topics. Machine learning has huge groups in companies such as Google, Facebook, and so on. But also smaller companies run a lot of computer science, even research-related topics in order to solve specific problems. As a research and industry, you would typically leave the system somewhere after step 2. But most scientists who work as scientists in industry, I would say, have completed their PhD degree. So I wouldn't drop out the bachelor just to become a research scientist at Google. Probably having a PhD would help you in the long run there. So as a case study, let's talk about something I know about, which is me. So here's an example of a resume that might end up on my desk, probably not as a PhD application, but just in general. So I myself, I'm German. I studied pure mathematics originally at the University of Bonn in Germany. I spent a year at Chalmers University as a research stay, but then I was most of the time at Bonn. I did my PhD there. Then I moved to a postdoc position in computer science, an internship at Google, another postdoc position at the Max Planck Institute in Tübingen. I was an assistant professor then at ISTA Austria, where I'm now, and since 2015, I'm also a professor there. So what is noteworthy about this? Well, first of all, I did complete all the steps that I had on the previous list, right? Master's, PhD, postdoc, assistant professor, professor. And one thing that is noteworthy is that I switched my field, and it's quite a drastic change. So my PhD was in pure mathematics. If you know pure mathematics, that's not something where you need a computer except to write email, or maybe a paper. I didn't write papers during my PhD, actually. But then my postdoc was in computer science. And not any computer science, but rather applied computer science. So originally, the papers I wrote looked like this. It was in complex analysis. This is a page for my thesis, one of the simpler ones. So it has fancy formulas. It has lots of black and white stuff. And then I switched to become a postdoc in computer vision. And what I wrote down looked like this. You suddenly had like plots, and you had pictures of animals. So it's not a small change that happened there. Then I moved into machine learning, where again you have a few more formulas, but it's still a very different working style than in a mathematical group, especially on a topic such as complex analysis, which has a 250-year history and emphasizes beauty over empirical relevance. So actually, that's not a problem. Don't worry. A lot of scientists changed their field. We had examples in the summer school. You hear, half of the professors at our institute studied something else than what they do now. Sometimes they switch after the bachelor's, from physics to biology, from math to something else. Sometimes after the master's, after the PhD, sometimes even as faculty, changing research directions in computer science. If you are a good, scientist is not so terribly difficult. Also because it's not just about memorizing facts, right? But scientists have some kind of soft skills about how to do science, which is much more compatible between disciplines than the actual facts that you might have memorized. Let me say that, so this lecture will not be 90 minutes. There will be plenty of time for discussion, questions, and so afterwards, but you can also happily interrupt any time in between, because it's meant to be an interactive session of like information, not me just talking a lot. So maybe later.
For questions, we want you to use microphone, then it can be recorded, the question. So
yes,
I need
just
to develop some
hand.
eyes to my back, but let us know.
Raise your hand anytime. So, I'm happy to get feedback so that I don't just talk to an empty room. Yes, please, finally.
Do you know many people converting from the other disciplines into pure mathematics later?
No. So actually, it's much more common to switch from a more abstract to a less abstract field. So it's much more common to study, so go from mathematics into something else, such as physics, computer science, or even biology. It's also much more common to go from physics to biology and neuroscience, something which is more like down to earth. It's not, I mean, even physics is a rather mathematical field in that respect. It's much less common that you start with in real lab work. So our institute is an interdisciplinary institute, which is probably not an experience most of you, or I mean me included, before going there have. So there's people in lab coats who pipette, right? That's not something a computer scientist sees ever. So the field of science is much broader than one can imagine if you just study in one building at the university and so on. And the skills required are quite different. And how to be a good experimental biologist is not necessarily something where you can afterwards solve mathematical equations. There's people at the interface. So there's people who are both biologists and mathematicians, but it's not common. Okay, so the next noteworthy thing is that after the master's degree at Bonn, I stayed at the same university for my PhD. And that's actually not a good idea. The main reason was that I was lazy, and Bonn is a good university for doing a PhD. So I never really thought about, ooh, I should now change. But if you want to like optimize how you learn more, how you become a better scientist, and how you have a scientific career, changing the location is, it's not totally required, but it's a very, very good idea. So being at more locations means being exposed to more different things. And I mean, I didn't just stay at the place, I also stayed in the same research group. So I met the same people before and after. So essentially, I was not stimulated more, which would have been nice in retrospect. My master's degree, PhD, and postdocs afterwards were in the same country. Another bad idea. I mean, this is the time where you have to move between places then. So spending time abroad is an extremely stimulating but also important factor if you want to have a scientific career. If you are really, really in love with your hometown, that's fine. But going abroad for a year or 2 or 3 or 5 and then coming back is better than just staying there all the time. Again, the stimulation, science lives from a clash of ideas, from like people having different opinions, people having different skill sets that come together. Because in order to do new stuff, you have to question the old stuff. And if you're just at one place all the time, of course you can question stuff, but it's just more, it gives you a very different experience. I did an internship at Google, not in order to improve my CV, but because, I mean, if you get offered an internship at Google, why wouldn't you do it? It's fun. Internships can partially compensate, but it's a different working style. An internship is always just, I mean, I'm a couple of months here, I work on one project, I go back, but the mindset is a different one from being part of a real, like doing a PhD elsewhere. And then the last steps, I became assistant professor at the ISTA Austria. And then later I was promoted to a professor. And this is really an example of this tenure track system, which Europe doesn't always have, but it's most common in the US, but also, I mean, here, it's more and more that you're first an assistant professor, you prove yourself, and then you get promoted without having to move again. And it's a quite important quantity because, I mean, you become a professor when you're probably in your 30s. I mean, if you're lucky, at least I did. And you don't want to, I mean, start a new research group, develop everything by computers, or start a lab, breed mice, whatever you do in your science, and then 5 years later move to another place and having to start all of that from scratch. And also you might want to have a family and like maybe your kid is in school, right? So the system that you can become professor at one place and at least stay there, even if the first contract isn't permanent, is kind of good for the researcher at that phase. So there's always a trade-off between moving around in order to catch more experience and trying to go down to one place. There's a famous anecdote, which probably shouldn't be recorded here, but so there is some little animal in the sea, some sea urchin or so, which as a larval state, it swims around, it's a predator, it eats stuff. And then eventually it becomes its adult phase where it puts itself on a stone, it attaches itself on a rock, and then it digests its brain because it doesn't need it anymore. That is just needed for moving. And this is an analogy to the tenure system, right? So, but I'm not going to go into one. Good. So these are the career steps. And the one thing to keep in mind is that even though these steps are like possible, the competition is fierce. So academic research is very popular. People like to have the idea of just doing research for research's sake. So there's a lot of competition, and in the end, only very few make it. And just to give you the illustration, this is a figure from the United Kingdom, I mean, quite a while ago. So out of this pointer, so this is 100%. That's the people who already finished their PhD. This is the graduates of the PhD. Half of them move into careers outside of space. Science, sorry. Some are out of space, but most of them move outside of science immediately. Some stay in the system and have, for example, a postdoc position or something. This is across all disciplines. In computer science, it would be much fewer postdocs. But across all scientific disciplines, like half of them stay somewhere in an early career research. Some of them go into non-university research, such as industry labs or government labs. Larger fraction goes into outside of science careers. 3.5% become permanent research staff in academia, and only 0.45%, according to this statistics, become a professor in the end. So that's 1 in 200. I mean, these are the numbers that are published. I don't know how, I mean, of course, each field has a different statistics, but it just shows that it's a very, very selective process, right? Just because somebody wants to be a professor doesn't mean they will become a professor. There's a lot of different factors involved, and some of the things I'm going to tell you today might help to like push you on the right path. Please.
To me, these numbers almost do not add up in the sense that you need professors, educators with the PhDs and experience to educate bachelor's and master students. So in here, if we say that for 15 students, we need 1 staff member, for example, or for 10 students, 1 staff member, then you need to have enough academic graduates who stay in the academia. And these numbers almost do not add up. Somehow it seems that it's not, you cannot sustain this this graph.
Yes, so that is one of the criticisms, and the simplest statistics probably is that if you have only 0.5% of all PhD graduates become a professor, that means each professor is in charge of 200 PhD students, which I very much hope is not the case. These are the numbers from some surveys that people in the UK got. So probably there is others. So this is, I mean, academic professor is not the only one who can supervise students. Permanent research staff can, right? So if you put them together, you have 4%. That's 25 PhD students over the career of the scientist, which is 25 years. That might be doable, right? So it's not obvious, but the main point is it's competitive. Okay, so if you want to go into the system, and I can recommend it, how to have the best chances? Well, the first thing you need is to study at a good university, and probably you can check that off for everybody in the room. The next step is to go and do a PhD at an even better institution. As I said, changing locations is important. So try to go abroad. I know, it's annoying, but it's worth it. You should, when you look around for where to do a PhD, there's probably the easy option that your supervisor tells you, why don't you stay? But try to aim high. If you go for a scientific career and do a PhD, probably you're among the top people of your university. You're at a good university. That means you have chances elsewhere. The usual step is that you apply to several PhD programs, not hundreds, because then you would just send an anonymous spam application, and I mean, people notice if you don't really care about the place. So one has to tailor and really select the programs you want. Typically, you choose ambitious positions, ambitious programs, and then you have a few fallback options such that when the ambitious ones don't work, you're not unemployed in the end. You can select based on your interests, but don't be too narrow-minded, because one big observation is that if you study at one place, you're exposed to ideas from one place, and you think the whole world, I mean, centers around that topics, but there's a lot of things that you probably have never heard of and that might be exciting and even better match to you. So be open-minded about what to do research on. As I said, you can change directions. that is totally fine. And we often have the case in our graduate school that people come in, they say, I really want to work with Professor X. And then they work with Professor S in a little project, and then they work with Professor Y, and then they work with Professor Z. And in the end, they join the research group of Professor Z instead of A. And this happens in my field, I mean, but it also happens across disciplines. Interdisciplinary projects emerge. So it's easy to be overconfident about opinions just because you don't have the information about uncertainty and what is out there. Good advice is to start early. So if you haven't gotten a PhD position yet and you're looking for one, typically the programs have deadlines almost a year before the start date. So you have to be aware that it's not enough to wait until your master is done and then, oh, where am I going to go? But if you want to have better chances, you have to plan ahead. So where should we do a PhD? I mean, of course, for the ones who are already in a PhD program, I mean, by all means stay. But for the other ones, or for friends or colleagues or whoever you meet later, strong universities are really not that rare. So strong universities exist on every continent. I found some. But if you want to find them out and you're not aware of them yet, especially in other countries where you don't know the system, typically what you go to is like a university ranking, right? So like, what's the best university in Europe, or what's the best university in China, or whatever you prefer. These rankings typically do not tell you much about PhD education and research. They're usually targeting for undergraduates. So there's other resources that look more at the scientific output, and all of them are not perfect, but they at least tell you a little bit more about what kind of scientific output comes out of the place. And since the publications are all written by PhD students anyway, that just means where are the PhD students most successful and most innovative about research. So there's a webpage, CS Rankings, which just ranks all of computer science places they can find by their publications. And then you can filter this and so on, look for places. And in the places, you can look at which faculty work in which subject area and so on. If you have already a field of interest, such as machine learning, you can, of course, check who is publishing at the top venues. But don't look for individual people, because that just might be a very, short-term view. And if a year later you apply, that person might not be there anymore. And also, they might not take students. So typically, one should look for clusters of strong people, right? Some universities have many good professors. Some have just one who happens to be there because, I don't know, his partner is working in the nearby or something. And if you don't want to look too closely to individual people, it's often a good idea to look for networks of excellence that universities and other institutions are a part of. So in particular, in machine learning, the ELLIS network has recently been established. Some of you might have seen it. So this is already some kind of mechanism where people, like-minded people, come cluster together, and then often this means you can connect the dots and identify promising locations. This is the CS rankings page, just to show you how it works. So you have all the different subject areas. There's a few more down here that didn't fit on the screen. And then whatever you activate, it will look at who publishes at the top venues, how many people, and you get this ranked list with, not surprisingly, Carnegie Mellon University and some other suspects at the top. And then you can check, of course, for different regions. So you can go by country, you can go by continent. And if you go to Europe, and you can click on also each of the individual places. So if you click on our place, then you see the individual faculty. And then this is the number of publications they had in the indicated subject area at only the top conferences or journals, depending on what it is. And then some kind of adjusted average that divides the total number of papers by the number of co-authors. Because in some fields, you have 50 co-authors, and that means the same paper would otherwise be counted 50 times. And then this is aggregated by some magic, and it gives you a total number. And at the same time, it tells you the number of people, so the number of faculty members who contributed to this. So you might also have to compensate a little bit that some places have 100 professors in this field, and some people only have 30 or just 2. So don't go just by absolute numbers, don't go by relative numbers, but just make yourself an overview of who is there and what they do. For each of them, there's also the subject area, right? So Krish is in logic, Bernd is in graphics, I am in vision and learning, and so on and so on. So it's automatically extracted from the publication records. So it's a very almost unbiased source. Of course, the mechanism to aggregate can be criticized. The other thing I mentioned is these networks of excellence. So the ELLIS Society is a recently established group which is like from scientists organized bottom up to support machine learning and related areas in Europe, especially in comparison to places like the US, where you have the huge labs and Google on top, whereas in Europe, it's often very isolated clusters doing good research. Also, China is investing billions from the government side. In the US, they invest billions from the company side. So ELLIS tries to like create some kind of critical mass to put Europe into the leading group as well. And they run a PhD program. So you can apply to the ELLIS program, and then this is like a meta program where you can apply, and then it will basically be matched to different universities that would match your interest. The ELLIS program you can become a member as soon as you have like a certain scientific profile and a PhD, but it's also organized in local units. And a unit is just a university or research institute that has a certain enough critical mass to sustain excellent machine learning and related research. The closest nearby is Helsinki. There's very little in Eastern Europe so far, but this is going to change. So probably Bulgaria will get one soon. It's a question of like putting together the critical mass and the funding that you can like convince the ELLIS organizers that you should be listed. We are down here, so we're pretty far east compared to the others. So then, if you already know a place, how do you find a good supervisor? And this, again, is a multifaceted problem. Scientific quality definitely matters. I mean, if you are an excellent scientist, that doesn't mean you're an excellent supervisor. But if you are a mediocre or terrible scientist, you will probably not be able to teach a student to be an excellent scientist, right? So it's a necessary but not sufficient criterion to be scientifically good. As stupid as it sounds, the past is still a good predictor of the future. It's not perfect, but if you see a research group where no student has ever graduated and everybody became an Uber driver, maybe that's not the right group to join. If you see a research group where everybody became faculty at Stanford afterwards, maybe that's a better place to try to get in. I mean, of course, it will be competitive, but just in terms of what to target, you can look at the graduates and see, is this profile something I would like to be, right? So, for example, a lot of my students joined industry because, well, it's very attractive to work for Google and Qualcomm and Amazon. This is something to keep in mind, right? And finally, the best advice I always give everybody, including the people who apply to our institute, is contacting the supervisor is, of course, a good idea. You should do that. But they are overwhelmed. They get hundreds of emails per week or maybe per day. You're just an anonymous email address to them. So the chances that they will give you a detailed exposition of what is good and bad about their group, especially what is bad, is not that likely. Talk to the group members. The group members are much younger. They have more time. So ask them how the supervision is. Ask how often they meet their supervisor. Ask if they do stuff together or if the supervisor just like puts the name on the paper and then leaves again. So this is a much more, this kind of student-to-student peer network is a much better source of information than asking the big shot professor if he is or she is a good professor. I mean, of course they say yes. Okay, so now you've probably isolated some kind of place. You probably want to start a PhD. So what should you look for in a PhD program? And because that's the only case I know, and because I like to advertise it, I'm going to use our own PhD program as the running example. So first of all, there's different formats of how you can do a PhD, especially in Europe. So there's the traditional European master apprentice system, which means you want to do a PhD with Professor X. You send a letter to Professor X. The Professor X sends you a contract, maybe talks to you first, who knows. And then you get hired to work in the research group of Professor X. And that's a very successful system. It created people such as, I don't know, Leibniz and Einstein. But it has a certain disadvantage if you, because you have a very highly dependent relation on your supervisor, right? So you're like a direct employee of the supervisor. If the supervisor decides to move to another city, well, you're either fired or you have to move with them. Or if they stop liking you, they can stop paying you. So this is a bit of a dangerous. It has advantages. It also has disadvantages. The US system works very different, and there's a bunch of graduate schools that now pop up that try to give more support and more power to the students themselves. So often it's not the professor individually making the decision to hire, but it's some committee or it's the graduate school itself. Afterwards, you're an employee of the graduate school, you're not an employee of the professor or himself. There can be a time where, because you don't get paid by a specific professor who needs to get their research done, but where you just part of the graduate school, there can be a phase of taking additional courses to catch up or to specialize, and to do different projects in different groups. And sometimes there's an unaffiliated phase where you don't even know who your supervisor is going to be. Often you can enter with a bachelor's degree because this initial phase will get you up to speed. And sometimes you can get a master's degree on the way. Or if you want to drop out after a year, there's an option to not drop out without anything. And this is the corresponding format from our program. So there's two phases. The first phase is unaffiliated, where you take courses, you have additional coursework, you have mandatory coursework. In particular, we have this core requirement where all students from all disciplines go through one program together. It's an interdisciplinary program. They take the same course, talk to each other, and you become friends with them, it's a cool thing that typically in the master apprentice system, you don't have this exposure to all the people. So I like the graduate system better, I have to admit. You do a project with different research groups, and then one of them you affiliate with, and then there's a so-called qualifying exam that means now you are ready to start independent research on your own, publish papers and so on. The second phase consists of doing research, some experience in teaching as a teaching assistant, progress reviews to check that you don't disappear from the radar. So for example, when I studied, this system did not exist, and there were some people who they didn't make much progress for a while. That happens, right? Everybody has that problem in their PhD, or many people do. So, but then they were a bit shy, and they didn't talk to their supervisor because they were ashamed to say, I didn't make any progress again. So then they didn't go to the supervisor. And after a month, it starts to get awkward, and after 3 months, it would be just embarrassing to go. Right? So then they just stayed home until the contract ran out, and they never graduated. Right? And some mechanisms to prevent that are kind of a good idea. Finally, you get a hat. So we actually give hats like that. It's good to sometimes remember that graduate school is more than a job. So it's not just a way of making money, right? Otherwise, you would be in industry and make more money. There is a personal connection needed. Your supervisor is, well, your boss in the end, but also a mentor who should have the goal of supporting you and your scientific career, right? It's not just their own benefit, it should be also for your benefit. So that needs trust, right? You get team experience if you work in a research group that, if you work in a bank, might be a very different experience. And you also get feedback or ideally advice from external sources such as a PhD committee or scientific collaborators, which is an important part of growing as a scientist and becoming better and more independent. In this graduate school system that we at least have, you see that there's a very strong feeling of coherence or belonging, as we saw yesterday on one of the posters, because if people from many different countries, for us it's now over 50 countries, come together in one place, everybody's lost. Nobody has studied at the same place. So you form a peer group, and this peer group might be people you otherwise would have never talked to. Right? So we have people, experimental biologists, who get friends and have board games nights with mathematicians, and then later in life they will just stay connected and do cool stuff. Okay. At the same time, grad school is also a job, you have to admit, right? So, and PhD students are highly trained, far trained and highly qualified, well, somehow scientist, almost finished scientist. So one should check that you actually get paid for your position. That sounds completely obvious, but a lot of the grant agencies, or many universities also don't give you a full salary. They expect you to work 40 hours, that they pay you 30. And in fact, the time a PhD student spends on the PhD is not 40 hours, it's on average 60. So you're paid for 30 hours, even you work twice as much. Doesn't feel fair. What's the status of the PhD students in the institution? Are they just a nuisance, or are they part of the teams and supported, for example? If they want to travel to a conference, do they have to beg? Do they have a budget for themselves, or something in between? And so What's the general attitude towards PhD students? Are they seen as just students? Are they seen as finished researchers? All of that is good to know before you actually want to join a place. Benefits, of course, if you can get subsidized housing, you're going to save a lot of money, these things. And also, like, what's the life outside of the science? Not every, I mean, you do work 60 hours a week or maybe more, and you sleep a few, but there's still a few hours left that you can spend. And then if you have some kind of social attractive institution, it's kind of more interesting than if you were in the middle of nowhere. So the final slide, which is of course the most pretty, is then this means why also location matters. So of course we are social beings and we like to be in places where we enjoy ourselves, and it does make a difference if you live in the murder capital of so-and-so where you need a police escort to get to university, or if you live in a place such as Tartu, or in Vienna, or in Helsinki, or something other place where you actually can have a good life. Questions?
I have this question that we cannot change our geography. We cannot easily change the size of our country. We can't avoid that there is very few universities in here for 1.3 million people. So many of the things are something that small countries or Central Eastern European cannot change, and I think there needs to be some big change of attitudes somehow in Europe to be more inclusive also in this kind of thinking, because now it's a little bit like strong get stronger approach, while in here we need to do everything, and we need to spread excellence more, actually.
Yeah, so you're right. So I mean, the presentation I give is a very biased one because it's from the position of the student, right? There's always the side of what's good for science in general, what's good for the scientific institution, and what's good for the scientist. And these are not always aligned, right? So, I mean, my advice is if you are a student who wants to have a scientific career, go abroad. You can go back, but go abroad. The local institution will probably say, don't go abroad, I want to keep you. I want to keep the best student around. But this is kind of, it creates a less diverse and more inbred system. And ideally, everybody would send the best students abroad and get the best students from elsewhere. And this is where the kind of imbalance happens, that like the most popular and most famous places get more of the good students, and the least famous or smaller countries get less. Like probably there's not so many people coming from Spain to study here compared to, I don't know, or not too many people who live in Zurich come here to study, then the opposite direction. Yes, that is unfortunate. But from the position of the student, I don't think my advice would be, well, you should support your local community, so don't go abroad. Then I'd rather say come back.
But even the CS rankings, for example, does not have Finland in there, and Finland has traditionally strong computer science as well.
But this wasn't all computer science, right? This was just the disciplines that are activated for our institute to look good.
Yeah, but I think the site still does not have anything from Finland.
Oh no, it has plenty of stuff from Finland. I mean, it just loses the DBLP. So where's Europe? Okay, it's not on the top 9 here. But if you go to the webpage, it should be there, because as soon as you publish in a top venue and have a Finnish affiliation, you will end up as a Finnish. I mean, otherwise, it's a big bug in the system that we should report. It's on GitHub.
Finland does not appear in the list of countries even there when you look at the top in there.
Well, that's a bug, right? Because Estonia does, right?
No, Estonia is not there. No? In CS rankings, no.
Well, it's a GitHub page, so you can upload it. Sorry?
Both are there. Finland and Estonia. Yeah, Estonia's there, yeah.
I have different. Okay. I'll see you.
Maybe it's not sorted because it's first continents and then. Yes, but that's first there's USA, then there's. Interesting. You have a much shorter list than other people. Is it a Mac?
Yes.
Macs don't speak Estonian, apparently. It should be on there. So maybe it depends on what fields you... No, you have all fields. Weird. In my list, I think it should be. It's going through the DBLP, and it regularly downloading it. It's some automatic scripts that extract the affiliation. There's a big database on GitHub where you can like edit who is an outlier. So.
No. Use the microphone, please.
I just wanted to ask quickly, what's the top venue? Because I checked the since we are talking about this, I checked the people who published in top venue at the University of Tartu.
Yes.
And well, it's a very short list.
When you go to the list of subjects on the left, on the bar, you see, I mean, I can't because it's not interactive, but somebody else can. Then it always lists like 3 or so main conferences or top journals. So for machine learning, it's ICML and NeurIPS, and then there's also KDD in the machine learning list. For computer vision, it's ECCV, ICCV, and CVPR. For embedded systems, I have no clue. For programming, it's probably POPL, and I mean, so the scientists from that community more or less say, like, let's use these. And on purpose, it's not using all because everybody thinks all of them are good, but it's really picking like 2 or 3 top venues. This is under heavy debate. If you go to the issues page, of course, they say, well, why isn't this and that there? But ultimately, one has to make a selection, and I don't think it's, I mean, you could game the system, but probably it's not as important to game the system that way.
Journals are not included at all.
I think this one not, or I haven't checked, not for the subject areas where I know anything about. But in computer science, I mean, journals play less of a role, at least in the fields that I do. Maybe in the theory side it's more, but I don't know. I mean, you can criticize this thing. It's much better than the Times ranking or so, right? Which doesn't look at science in this kind of form. I mean, it's not meant to insult the university that's not on here, right? It's trying to give some indication. It's never the only criterion, obviously.
Okay, so you switched fields, and my question is about which math content specifically has helped you the most afterwards, after the switch as well as which more specific broad skills supported the change, or which you've really made use of?
Yes, I mean, I like that. Oh no, I shouldn't tell that on camera. So I mean, as many things in science, this was a coincidence. I studied complex analysis. I liked it. It was very pretty. It was always a bit old-fashioned. And in parallel, I was a computer nerd. I was programming. I was like using my computer, downloading stuff from the internet, and so on. And ultimately, I noticed that I was spending more time on the computer than in front of the desk. And I decided, well, maybe computer science is not the worst thing to try. I was looking for postdoc positions in both mathematics and computer science. In mathematics, there would have been like a scholarship for a 50% position where I would have had to change fields completely. And it wasn't offered to me, it was just mentioned. In computer science, I got an offer for a full position from a research institute that was decent, the DFKI. And my boss there basically said, well, you're a mathematician who knows how to program. That's enough to have success in computer science. I didn't mind. Out of my math skills, well, knowing numbers, summing them together is a useful skill. Not being afraid of abstract concepts, vectors, why not? Matrices even. Taking a derivative helps. Of my PhD stuff, nothing. I mean, absolutely nothing. Every couple of years, I try to say, like, shouldn't I include this in somewhere in my research? But no, there's no way. The one thing I should have taken as a math undergrad was statistics. But that's the one subject that wasn't mandatory for mathematicians. Computer scientists had to take it. So all of what I do now is somewhat based on statistics. It wasn't the perfect change. But of course, I mean, as a mathematician, you learn a lot of other soft skills, as you say, that are very useful later, like logical thinking, like formal thinking, how to refute an argument, how to construct a minimal working or non-working case in order to get an argument across, how to, I mean, break things. Whenever I see a definition, I have the tendency to immediately try to break it, right? Because like well, what about this? Isn't that a bad thing? And then this helps a lot to like not try to do things that in the end won't lead anywhere. So tolerance against frustration. Math PhD is a lot of frustration, and then 3 months later, you still haven't made a single line of progress, and then suddenly you have something, you're very happy for a day, and then the next 3 months start, right? So these are skills that you learn during a PhD in many fields, which you will need as a scientist later anyway. So.
You briefly mentioned that you didn't write articles during your PhD. How does that look, and is that optimal?
that is beyond suboptimal. It wasn't, I mean, that is terrible. But so as I said, the field I was studying was quite, traditional in that sense. And the goal of the PhD was to write a PhD thesis, which contained the work that you did during the PhD. There was no culture of writing publications about intermediate results already during the PhD. That sounds very exotic now, but that 20 years ago, that was just how this group operated. Other groups operated differently. So in the end, out of my PhD, I have like a book, and I have one result that I tried to publish in a journal afterwards, but that actually just appeared after my first computer science paper had accepted. So it's a long delay, and it's not, I mean, it's maybe cited 3 times by now. So I wouldn't hire myself, right, at that stage. But the times have changed as well.
I have a question about this lab rotation thing. So you admit the PhD students into the ISTA, and then you allow some rotation for them. But then even in Europe, there are these initial training networks where there are very specific projects announced. And we at Tartu, we are at the moment with the system stuck that we have to advertise very specific projects. So there is no concept of this kind of lab rotation in the beginning. So what is your take on this? How you advertise the positions in generally, or ITN networks? And is it the project specific, sort of very clear that this is going to be my topic, and I have a click, versus I'm going to wander between cryptography and machine learning and figure out what I will like to do?
Actually, a student who rotated with me then joined the cryptography group instead. Pity. So for us, basically, this phase 1 is, I mean, if we have grants or we have projects that have specific PhD positions, they are part 2. So part 1 is typically not funded by this kind of projects because, well, the funding agency don't want to fund a student who just idles around and pipettes and so on, right? So the first phase is typically funded from institute funds or from some other specific European grants that would be dedicated to funding this kind of PhD school. So we had a grant from the EU which funds like 40 positions for 4 years. Well, you can convert that, if you argue well, into 160 positions for 1 year. And then that wasn't tied to a specific topic. But of course, the funding situation is always something one has to take into account. Again, this is from the position of the student. The professor, of course, has much more restrictions in how they hire something. And so the ELLIS program that I mentioned, this is a meta program where you might end up in any of these different places in the end, not just the units, but also others. And then it's really a mess of like, Berlin has to advertise a specific title of the thesis. Vienna doesn't, right? So this is, then there's always some kind of local adaptation needed. But the general principle that the students are able to make a choice which group to join after having seen different options. So for us, that is very important. And that's directly taken from some US universities, such as Berkeley or so. So there it's much more common that you're free floating for a while before you affiliate. Europe isn't really doing that so much.
So in one of the slides, when you talked, you heavily recommended that going abroad would be a useful thing because sort of you're exposed to new stuff and it helps you out. But yet when talking about changing fields, you said that it's not terribly difficult, but could there be like an advantage there also being exposed to like other stuff from other fields in the long term?
Yes, so I like being at an interdisciplinary institution because you will hear about stuff. I mean, the stuff I learned about biology in the first year that I was at that institute was very different from what I learned in high school. I mean, everything I learned in high school is wrong. Right? First of all, much too simplified, and second, probably wrong anyway. So it's very stimulating to be like change fields or be in an environment where people do different fields, and this idea of interdisciplinarity is, of course, extremely attractive. The problem with it is that it takes a lot of time to learn a new field. I mean, not 3 years as it would have been in math for me, but you need a year or so to really get into the field and understand what people even care about and what the new is. And if you're on the clock and you have to graduate after 3 years or 4, then probably it's not the best idea to change fields 3 times. If you are an interdisciplinary person and you want to combine 2 things, that's great. But for many people, it's about going into depth as quickly as possible to make progress, and then doing something else is a distraction. This is it's a personal choice, I would say. Change in location is different for me because you speak the same language, which is, I mean, the universal language of English is bad, of science is bad English. So everybody's, I mean, you go somewhere, if it's the same field, right, you have the same words, so it takes much less time to adapt scientifically than it would if you completely change fields.
Thank you. I have a quick one here. By the way, I just wanted to say big thank you for a great talk. I don't remember if anyone said that before, but just to be sure.
Still stuff, don't worry.
Regarding this rotation system, I know as a matter of fact that this might happen that the student is not affiliated at the end of the rotation sessions because maybe nobody actually want to invite them. Can you comment on this? What happens to these kind of students?
I mean, there is a qualifying exam. This pointer. So there is a qualifying exam, again, copied from the US, and it's possible to fail the qualifying exam. Much more common is actually that you drop out before because either you don't find a group that you want to join, or you pick a group, or the groups that you want to join don't want to pick you. Or, and that is actually more common than the other cases, you just notice that science is maybe not for you after all. So, I mean, life as a scientist, it depends on the discipline, is often different from what you expect after your undergrad studies. And this first phase is also a way of like learning what research is. And if it's not for you, then you lose half a year or a year, but you don't lose 5 years by never graduating. So I think in terms of numbers, we have like 10% of people who do not make it from phase 1 to phase 2. And the main reason is that we're highly selective in phase 1. So you can't just get admitted because you have a good CV. But one of the faculty looks to the case and says, this is a student, after the interview, I want in my group. And of course, it can happen that you have that impression, then you talk to them, they are a jerk, one of them, and in the end, it doesn't work out, but it's rare, right? So, and most of the cases when people join and want to join a group, but then don't, they find a different supervisor because these are good students. I mean, we hire them because they are like very promising. And as I said, it's not so hard to switch fields a little bit.
Do you have a take on research institution versus university? So all the Max Planck Societies, CERN, EMBL, ISTA, I guess, as compared to some classical universities, because the environment is quite different. So what's your take on that?
It's a dangerous question because I'm a big fan of the research institute where I am. For faculty, it's great to be at a research institute where you do not have to teach courses that you don't want to teach, which happens at universities all the time. Right? Somebody has to teach Java 101. Nobody wants to teach Java 101, but somebody has to, right? I hope I didn't insult any Java teachers. For the students, I think the difference is not as big. So I think research institutes tend to be smaller and slightly less anonymous. But again, once you join a PhD program, you're typically in a group of 10, 50 people, whatever. So it's not that this is an anonymous mass anymore. You stopped being like a number and you start being a person with direct contacts and so on. So then I would rather see it as a question of funding. If you have a well-funded institute where you have your own cryo microscopy thing, it's better for your research than if you're at a place that has no money for that stuff. But I don't think that this is necessarily a question of research institute or university. I mean, there's well-funded parts of universities and there's badly funded research institutes. So I wouldn't say that this is it's a major thing. One thing to mention is that almost all research institutes are not allowed to give PhD degrees. So in particular, Max Planck and so on, they cannot give you a PhD. They can only like tell you, here, this professor at the university, they can give you the PhD. And that sometimes creates a conflict when the topics don't match up, because in the end, you have to defend a thesis with somebody who's not your supervisor. You might have never met them before. That's a bit awkward. But again, this also depends on the local place. Some places have no problem with that whatsoever. In some Max Plancks and some other Max Plancks, there's tension.
So I'm wondering, how much have you seen of someone going to the industry after masters, perhaps, and then spending 1 to 2 years there and getting into PhD program, and do you think that makes a difference in their performance?
So yes, this happens even more after the bachelor's, I would say, but also after the master's that people work. Typically, you don't work as a scientist in industry, but you work as a developer or engineer or something. Right? So I don't think many people work as hardcore scientists and then go back to grad school. It's a slightly different profile. It has advantages and disadvantages, right? One of the advantages is that you have much more experience with doing things and getting stuff done. I mean, overgeneralizing, of course. So if you just do your homework every weekend and you fill out that the answer is pi over 2 and then you go home, that's not something that will help you very much during science. Whereas if you have projects and you have learned how to make yourself deadlines, you just aged a bit, got more mature. That's a good quantities for doing a PhD. The disadvantage can be that maybe you are out of the learning zone. So if you spend 5 years in industry and you haven't opened a book during the time, then it's very hard to sit back down and try to learn something completely new from scratch. At least, again, overgeneralizing. So, I mean, these are cases that definitely exist. Again, in the US, it's much more common, or outside of Europe, I mean, other continents as well. In Europe, I think it's much more streamlined that many people don't go into industry and come back because it's more seen like once you're out, you stay out forever. But, I mean, in principle, nothing speaks against that. As I said, it depends on the length and the topics and so on. Okay, I have to continue because otherwise I don't get to my favorite slides. So now you have decided to go into a PhD program. What do you have to do? So you have to, it's definitely hard to get into a strong PhD program, or at least into the best possible. Ours has an acceptance rate of 4%, which can be misleading because clearly not everybody of the people who apply have a chance. There's just people who apply, because they have never heard of our place and they decide to apply everywhere. But ultimately, out of the 2,500 applications, we interview like 200 people, either online or on campus. We make 100 offers, and then 2/3 of that accept. In computer science, it's less than 2/3. So it's a small number that remains out of a large number of candidates. And this is not that different at other places. I mean, there's many more applicants than there is positions, obviously. So how do you maximize your chances? Well, one thing is to take it seriously and prepare. Look at what the place wants, identify programs, be informed about what you have to do, because when you violate the conventions or whatever the place asks you to be, then typically that doesn't make your application more highly ranked in the end. At the same time, because it's a numbers game, try to stand out from the crowd. So talk to potential supervisors, go to summer schools and talk to people, right? You stop being just an anonymous email address and you start being a name or a face even. And that means when later these things are evaluated, somebody might remember you, which creates an unfair bias for you against others. Internships are a great way of finding out about other places. And in general, an internship is something that you can often squeeze into the regular studies, and nobody objects to doing that. So it's a way of getting to know new places, but also to have a first connection to a new place that you might later want to study. Also to write your recommendation letter, as we'll come to later. And then the application material typically consists of more or less these 5 things. You will have to submit a resume, transcripts of your grades, statement of purpose, some kind of reference letters, referees, and sometimes a language certificate or some kind of other formal thing that you are allowed to, or that you are able to join the program. And each of these you can do well and you can do badly. So let me give you some positive and negative examples. So the resume is, again, this is my experience. If I would apply to our institute or the institute where I was before in Tübingen or DFGI in Kaiserslautern, I would do this. So a tabular resume. Don't write a long statement about your resume. 1 to 2 pages in English, inverse chronological order. I don't care how you went to kindergarten, right? I want to see where you went to university. You do not need to include personal data such as your grandmother's name or what you do as a hobby, unless this is a super relevant hobby, such as, I don't know, if you apply to be a scuba diver, then probably scuba diving is a good hobby to list. But if you apply to computer science, probably there's not much you have to tell me about your hobbies, right? Why would that influence my decision? Education is more important than work experience in this respect because the PhD is still some kind of learning process. Any additional things to stand out from the crowd, absolutely desired, right? If you win a medal at the Math Olympiads, well, put it in, right? So not the medal, but the statement that you have the medal. Or put in the medal, that would be fun. So this is what a real resume from our institute looks like that was successful in the end. You can't read it, I hope. No. I tried to blur it enough so that you can't read it. But this is a completely decent statement. I mean, it's completely decent resume. Transcripts, nobody likes grades, but bachelor and master grades do matter in some respect, because everybody who reads your application in the end is lost. They have no clue about you, right? So they need to have very simple pointers why they think you would be a good student. And good grades is just a very simple criterion for that. It doesn't mean that mediocre or bad grades couldn't be overcome, but it's just very useful if the first impression is, oh, top student. If the grading system is complicated, then helping the reader, again, if you apply in a different country, they might have a very different system. Germany, for example, the grades go from 1 to 5, but 1 is the best and 5 is the worst. Other countries, it's the other way around, right? So if you say, I had a 1.2 average all my life, then people in other countries might be really upset what a bad students you are, right? So help them to understand, because ultimately you want to convince people that, I mean, to look closer at your case. And it's your job to kind of explain something that they are not familiar with. Translations help if it's in Cyrillic letters. I will not be able to see which courses you took. If you translate it for me, that would be very much appreciated. Some PhD programs give grades as well. Those don't matter at all. Nobody cares about those later. Statement of purpose is a statement that writes on 1 or 2 pages, like, why do you want to do a PhD? What is your interest? What have you already done? And so on. Why is this institution something you want to pick? So if you just say, I always wanted to study at ETH Zurich, but then you send this application to our institute, doesn't make a good impression. What research are interested in? What do you have done before? It's also a way to explain things that don't look perfect, right? So if you had to take care of some relative for a year and you have a gap in your CV, right? I mean, just explain it, that's fine. I mean, nobody judges for that. Maybe it counts as a positive. So this is a good place to do anything. My advice is to not lie. That doesn't make a good impression if it comes out in the end. Be honest, but don't be modest. Don't say like, yeah, I'm just one of many students and there's so many smart people in the world. I never thought I was smart. Don't do that, right? You have to be bold, because ultimately chances, I mean, so there's statistics that intelligent people think they are less intelligent than they actually are, whereas non-intelligent people think they are more intelligent than they are, right? So you can check which one is true for you. This is a statement of purpose that looks good. This one is too short. This one is definitely too long. These are all real cases. So somebody sent like, in my PhD, I want to work on the following topic. This is the first paper I'm going to write. I'm going to solve it with this method. Then I'm going to work on that project, and then I'm going to work. When you apply to grad school, you will probably not have a clue what topic you're going to work on exactly, and you definitely don't work which paper you're going to publish in which year, right? So this just shows that you don't know what a PhD is, or that you just take a grant proposal and submit it. But it's not adapted to the task at hand, which is good. Explain who you are and what interests you. Referees is a super important topic, unfortunately. Again, because the people who read your file don't know anything about you, and they are not confident about their decisions. I think that's pretty common. They're always very uncertain because they're not familiar with your person, with your research before, probably they've never heard of your university, of your supervisor. There's just too many places and too many things out there. So they will just rely on other people's opinions. It's a very natural thing, right? If somebody says that person is great, then you also think that person is great. So referee letters are meant to do that for you, and so for that they have to be strong and positive. Don't say, if you ask somebody for a letter, ask them if they can write you a positive and strong letter. If they say, well, but I don't know you well enough, I have to write a lukewarm letter, then try to ask somebody else. Because if the statement is, yeah, that student went to our university, so rather she's the smartest student ever, then she's okay. At the same time, they must be personal, right? So like, our university has lots of smart students is not a good reference letter, right? So you must have a person who personally knows you in order to give a credible assessment of your skills or of anything else. They should know you well, but they should know you well scientifically. And again, I'm not making this up. We get letters from the soccer coach or from the brother, right? So I've known my brother all my life, and he's a great scientist is not a strong statement. Well, it's better than nothing, but it doesn't cut it. And then if you happen to be in the luxurious situation that you have multiple people who can write you letters, try to be a little bit diverse such that the information is not redundant, right? So if one person says, got 89% on the machine learning course, and the next person says 89% on the machine learning course, and the next one says also that, because they're all the teacher of the three teachers that the machine learning course had, that's a bit redundant, right? So rather try to have people from ideally different places, at least different courses, different countries if you can, right? Because this just shows that you are kind of more, they have a better, shines better light on you than if it's like the people who sit in the office next to your lecture hall. And finally, the scientific reputation makes a difference. So if a Nobel Prize winner writes you a letter, it's probably better than if, well, a non-Nobel Prize winner writes you a letter. But that's not, I mean, ultimately, most of the letter writers we don't know, right? We do not know if this is big shot Professor X from, I don't know, Tallinn or not, because there's just too many to know everyone. We're not Googling all the supervisors to see who has a high age index and who doesn't, right? So unless they are super famous, which makes a good impression, it's probably more recommended to have a strong letter from some enthusiastic person than a lukewarm letter from the big shot who is like head of the department or head of the university or something like that. I mean, as you can see, this is not easy, and at the same time, these things do matter. So if you want to apply for any kind of program, it's not just for grad school. I mean, this is, of course, an explanation for the graduate school, but if you're looking for a postdoc position, it's not that different, right? You will need some kind of list, you will need a publication list on top, but you will also need external letters. So it's good to search for letter writers as quickly as possible, right? Try to find people who are willing to say something good about you. A lot of the applications fail because nobody has anything good to say about that person. Probably they are still good scientists, but just if you cannot prove or show that somehow, how would we know? Publications. If you do have publications, and that happens more and more, of course, during the undergrads already, or during internships, then by all means list them. For me personally, it was never a big criterion, because most of the publications that one writes during the undergraduates are not so scientifically exciting that the world would like not be able to move on without them. That was probably insulting, but it's a skill you acquire, and then unless it's like the top venue and you're the leading author and you did everything by yourself, then it's good to see that you were part of a team that was able to publish. That's an experience, but the actual content probably nobody will check. So list them, but don't think just because so for example, there's websites where students exchange information about graduate programs. One is called thegradcafe.com. And then the typical statement is, I applied there and already have 5 publications and still I wasn't taken. Well, just having 5 publications is not enough, right? It's a very minor factor out of many different things that enter the decision. And also because it's a very random process if you have a publication or not, right? If you happen to be in a research group where undergrads be part of research, then you're lucky, but it's not that you have a lot of choice with this typically. Okay, and then starting early is important because these programs have a very long delay. The application portals typically open in autumn, and because I've talked enough about our own program, here's the ELLIS PhD program deadlines. And then over the winter, you have to submit, there's interviews in early in the year, admissions maybe February, March, and then there's a more or less accepted deadline from many institutions that by April 15 is the date by which you have to make a decision whether you want to accept the position or not. And this is trying to be unified because otherwise people can try to game the system and say like, I'm making you an offer now already while you're still waiting for the other offer, but you have to say yes or no before you get the outcome from the other. And that's just a lot of pressure that, we want to avoid our students to be in. So we should, in theory, you can collect as many offers as you want, and then by April 15th, you have to pick one. That's the more fair process. Of course, that means that between April, when you actually get the decision, and when the semester starts, which is like September or October, you have a bit of a gap. Well, that's a perfect time to visit a summer school, do an internship, volunteer, building houses, whatever. Okay, so now it's time for a few more questions. And then I move on to the part that a scientist does after the PhD.
So a question a little bit about during the PhD and regarding doing internship or going for a research visit, how would you recommend, or what parameters do you think it's important taking into account that the PhD needs to end and the effort into any kind of research visit needs to be like towards the thesis?
So in general, internships during the PhD are very much encouraged, and in a sense, they should be tailored to what you try to do afterwards. So when you do a PhD, often you have an opinion, do I want to become a professor? Do I want to work in industry? Do I want to do a startup? Anything like that. So if you want to be an academic in academia afterwards, going to another place for an internship is typically a good idea. Maybe not 2 months before you have to hand in the thesis, but there's like, I don't know, a PhD is maybe 3 years long or 4. In the summer doing an internship and next year again, that I think is a good choice because, as I come to the very end, you will build up connections to other places that are extremely important in science. And you learn new stuff, of course. If you want to go to industry internships are amazingly important. So, I mean, if you want to work at Google, doing an internship at Google is half the foot in the door. So it's much easier to join a big, amazing companies such as, I don't know, Meta, OpenAI, DeepMind, if you already did an internship before. So I'm a big fan of my students going on internships. That said, there is, of course, constraints, right? Your supervisor might not want you to go because they have a project deadline. So if 2 students work on a project and both of them are on internships, when the deadline approaches, you're in trouble, right? So, that, of course, the circumstances, dictate that. Our experimental sciences, if you breed a mouse to be trained to go through a maze, then probably you don't go on an internship just when the mouse is ready to do its experiment, right? Common sense kind of rules. But if there is the opening in a theoretical field, there often is, I'm always in favor. 3 months is enough though, right? You don't need to go for a year.
Another question is a little bit different. So you mentioned that things like hobbies are not important on the resume. I understand at the first stage, probably there is too many things to consider. But when it comes to the social aspect of being part of the research group, like human interaction, like social aspects of it, teamwork, then when does it get important, or does it get important at any stage of the, let's say, getting on board onto the PhD or during it?
Yes, being part of a research group or being connected to the members of the research group is, of course, important if you want to do your PhD in the research group. So, one thing is, at least in our program, you go through these courses together with all students from the year, which means like 60 others, out of which in the end you will have like 5 friends or so or more, depending on who you are, regardless of if that is your research group or not. Right? But the main thing is that doing this rotation in different group doesn't stop you from socializing with other people, right? So you do a rotation in a group for 2 months. Of course, you get to know the people, you learn which music they like, you can talk about anything. And that means if you go on to the next rotation, you stay in touch. You can still go to the group meetings, right? You can still do the activities that they do. So typically people do not just do a rotation, drop out completely, and then 3 months later come back and say, now I want to affiliate with you. But the people who like the interaction of a group typically stay connected with the group throughout the phase, if possible.
My questions are about the requirements for the finishing of the PhD, for example, from your university. In my case, it's Tartu University of Technology, and in beginning, my supervisor said that I need to publish at least 5 conference publications. But at the same time, he gave me advice that we need to focus on the journal publications and how to say most high ranked journals, which is possible for my research. And so, what do you think? It's how to say it's international the requirements for the PhD student to have the specific number of publications and specific number of journal publications.
This is very difficult. some programs have restrictions, like say you have to publish exactly or at least 5 things or so. I'm not a fan of that because it's not hard to publish 5 papers, it's just hard to publish 5 good papers, right? So if you know you have to publish 5 things, you just say do 5 things and send them to the worst possible event in the world, and then everything is accepted. That's not a good criterion. Saying you have to publish 5 or any number of papers at the top venues in the field is also not a good criterion, because you might do good research, but it's rejected for some clearly, I mean, I'm going to talk about the process later. So you can do good research and it's still rejected. I mean, that's not, I mean, sometimes it's the fault of the student, sometimes it's not the fault of the student, right? So you shouldn't be stopped from graduating just because some reviewer had a bad day. So, my own criterion is I want to have the impression that the student is doing good research and is independent in doing it, such when they move on, they don't need me anymore to do good research. That's a very vague criterion, I know. But that means that if somebody did research that I think is really strong, but happens to be rejected, or the process of the publication is so long that, I mean, after a year and a half, the journal still hasn't replied, I don't mind. If my opinion is that this is a strong student and they will do good research when they move on as an independent scientist, I mean, they can put the stuff on archive and I'm happy with it. Of course, there is statistics that if you are a very strong student and you're having amazing ideas and you're brilliant, then chances are higher that you will publish lots of great papers than that you don't. But I'm not a fan of like hard criteria, which typically just turn into a nuisance, not necessarily pushing for good research. I don't have the impression that students are lazy and then just you have to say you need 3 papers because otherwise you would just slack off and play, I don't know, Counter-Strike all day, right? It's not why people do research. I mean, people want to write good papers. So I would imagine that this is enough of a criterion, but this depends on the individual university. It also depends on the individual supervisor. So it's very hard to come up with a general rule that would not antagonize people and make others unhappy. Okay, let me talk very, very fast about the rest, because we have hardly no time left. I thought this would be an hour shorter. I literally thought that after half an hour we would start the Q&A. So now that you are a researcher, what can you do? I checked some statistics, and I mean, it's very hard to find like reliable empirical evidence, so I'm going to present some anecdotal evidence. What do people spend their time on? Well, they asked a bunch of researchers at Boise State University with some kind of, well, proper psychological protocols, but not necessarily a representative sample who replied. And they spend a lot of time on preparing classes, doing administration for courses, reading emails, having meetings, and then somewhere in between you will also see research, right? So like there's reviewing, where's research? See, it's primary research. And probably that's the impression that most, at least faculty members have. So they spend a lot of their time on other stuff and they spend almost no time on research. If you cluster the stuff, of course, that is to be done, well, you find research is a part, including the actual research, including publications, including grant proposals. You will find that education is an important piece, obviously, because we're not just doing research, we're also educating new researchers. And administration is a part because, well, for some reason, administration always pops up, no matter where you are. As a PhD student, you clearly want to be in the research area, right? You do not want to write grant proposals and do administrative work all day. So it helps to ask others, well, how much of your time do you do research and how much of your time do you do other stuff? Postdocs typically move more also into the education area, and especially if they want to be faculty later. Education teaching is an important part of the job. So you get experience. Of course, you can get experience in teaching as a TA also during the PhD, but actually teaching lectures and preparing them and all the stuff that goes into that typically enters after the PhD more than before. In industry, you typically don't teach so much, but you have more administration because it's a company and you have a manager and so on and so on. And finally, as faculty, you do all 3. And of course, the big question is how much of each of them do you do? And my general guideline is that it's roughly 50% of the education, at least if you're at a place that teaches courses. It's 50% administration, and it's also 50% research. And that's because the average working hours of a faculty, I mean, of any researcher from PhD, postdoc to faculty is 60 hours roughly. So you work 1.5 jobs. The 50% includes grants, which I'll come to in a second, if I have time. So clearly writing papers is a big part, and you have this slogan of publish or perish, because if you don't publish, then you just disappear and, well, your career ends eventually. So either you publish papers and you become visible, or you fade out of existence. It's incredible how many papers are written. So 2.5 million new publications per year in this one statistic from UNESCO. And I checked, out of 5% roughly of these are in the area of artificial intelligence and robotics. So that's 150,000 papers per year, roughly in an area related to mine. Clearly, there's a growing trend. Within a couple of years, it went up by 35%. And the summary is that there's absolutely no way in life where you can stay up to date with all the research that is published out there. So you have to rely on other mechanisms to identify what papers to read, what science to absorb, or even which titles of the papers to read. And there's a few hacks that you can do, right? So you can just look at only the stuff at the top venues in your field. That's still probably a few thousand per year, still too much. And also you will not get an overview of everything that is done, but you will get the stuff that is successfully published at a top venue, which typically means there's some mainstream effect. You don't get the outlandish things that then 5 years later become mainstream. You can just look at the top scientists you have heard of and look at their web pages. That gives you much fewer publications, but probably it's going to be too narrow and you're not going to read everything that's out there, because most work is not done by famous big shots. There's some automatic aggregators, in particular Google Scholar, which are very useful. They're not enough, but you can enter keywords or names of people, and then it will regularly send you updates. Maybe some of you already do that. It's a good source to learn either stuff that is related to yours or stuff that, just has any kind of keyword that you're interested in. It creates a bit of a filter bubble, because a keyword you don't search for, you will not get sent anything, so you will never learn about that this exists. And finally, surprisingly much, at least for me it was surprising, a lot of science communication happens on social media these days. Well, you're not surprised. I was surprised. So Twitter is a big source of scientific news if you subscribe to some people who work in similar fields. There's aggregators who give you the most exciting stuff from arXiv and so on. The disadvantage is that this is highly hype-driven, right? So it will give you a few topics that make flashy pictures and sound exciting, but that other fields would be completely ignored just because there's no person who feels responsible for posting that stuff. So all of these make sense, but none of them alone is enough. As a young scientist who now is in a PhD, or afterwards, the advice would be to make yourself as visible as possible. It feels kind of bad to advertise yourself too much, but it's important that people read your work, and that won't happen automatically. So you need to have a scientific homepage. A LinkedIn page is not enough. A Facebook page is not enough. You need to have a page where you put I'm this person, this is my resume, I work on these topics, these are my publications. Otherwise, Google doesn't find you, and if Google doesn't find your name, you would immediately have a disadvantage. Google Scholar is a profile where you automatically have these kind of publications once you have them. If you upload manuscripts to arXiv, they will become much more visible and more easily multiplied than if you don't. As stupid as it is, a Twitter account where you kind of interact with scientific publication people helps. And just socializing and talking to people, going to summer schools, connecting to each other is a way of making your own research more visible. And only if it's visible, it can have impact. And if it doesn't have impact, again, you perish. This is the path of how a machine learning publication happens. Unfortunately, I don't have time to go through it. That's a pity, but you can have a look at the slides later. So the main thing is it's a complex process, and it takes a lot of time in each step. So the publication process, even at conferences in computer science, is relatively slow. It's a couple of months between the finished manuscript and when it actually officially appears somewhere. And arXiv over here is an established form of pushing the information about your work out there already in the very beginning when the project is done, before it's actually accepted. That means there's also bad stuff on arXiv, right? This stuff is not peer-reviewed. People do, it might end up with, wrong or misleading or anything else, but it's, the innovation cycle in computer science is often so fast that you go to a conference and the papers you see there are already outdated and have been superseded by other works that haven't even been published yet, and so Okay, some statistics, because I like plots. As you can see here, these are the ratings that papers get that were submitted to a conference, in this case ICLR, the International Conference on Learning Representations, one of the big machine learning conferences. And you can see that the distribution of scores these get from the reviewers is pretty much a Gaussian bell curve. So it's not that you have strong papers who get high scores, bad papers that get low scores, but it's all over the place. It's a mush. Still, you have to somehow separate these into accept and reject. And that happens here. So these are the scores of the accepted submissions. These are the rejected submissions. And you can see that the difference is roughly at 6.0 out of 10. So here, like up to, if it's above 6, there's a majority of stuff accepted. If it's below 6, the majority is rejected. And if you go back to the original, 6, where is it? 6 is the middle of the pack, right? So you basically cut through the Gaussian here, almost the middle. If one reviewer changes their mind by a factor, by like +1 or -2, this can have big impact on the average score. So if one reviewer says 0 as a score, it's almost impossible to reach a 6. Right? So there's definitely luck required to get reviewers who happen to give you large scores. The same paper could get high or low scores depending on who reviews it. So papers being rejected is not a shame at all. Of course, papers are also rejected because they're bad, but even good papers are rejected. NeurIPS, another machine learning conference, is kind of fun because they like to do little experiments to understand the process. And this is the so-called NeurIPS experiment that was done in 2021. It was originally done in 2014, and now they thought they should repeat it to see if anything changed. So they took out of their 8,700 submissions, yes, that is a scary number, they took 10% and submitted them in 2 copies to a completely disjoint set of reviewers and a disjoint set of meta-reviewers who make the final decision. And then they checked how consistent are these decisions. And as everybody had accepted, they are not super consistent. So overall, there's an acceptance rate of like 20-something%. And out of the ones that were submitted twice, like 2/3 were rejected in both cases. But then others were, half of them were sometimes rejected and sometimes accepted, or was, right? So if a paper was accepted in one of the stacks, they had a 50-50 chance to be accepted in the other. That's better than pure chance. If you had pure chance, you would have disagreement of 35% in this case. Here it's just 23, but it means that luck matters, and it means that scientific quality matters, and it's very hard to tell like which is the reason when you get in or don't get in. These numbers are actually consistent with the analysis from 2014, which means that at least the review process didn't get worse, because then the number of submissions was like 10% of this, so less than 1,000. Okay, so now I cannot tell you much about grants because the time is up, except that everything we do, everything I do, probably most of the people who have a position what you do, is paid for by grant money from many different sources. Can anyone have a guess how much money worldwide is spent on research? Show of hands. 10 million. Who is in favor of less than 10 million? Wow, that's stupid. 100 million, less than 100 million. No, that's still stupid. 100 billion. Who's less than 100 billion? 1 trillion. 10 trillion. 100 trillion. I don't think 100 trillion is possible. It's somewhere above $2 trillion, which is 2.6% of the world GDP. So, and if you think, another statistic says there's roughly 8 million researchers out there in full-time positions, or 8 million full-time positions of researchers. And if you divide that, that's 250K for every one of us, right? I wouldn't mind. I would take that. But that's not how it works. And most of this goes into corporate research. A lot of it goes into all kind of other programs, so it doesn't end up in my salary in the end. And instead, a lot of what research has to do is write grants. Writing grants is tedious, as everybody in the room who knows what it is does. You can have a look at the slides for some numbers. And in the end, let me summarize with a statement that hasn't shown up much before, and that is that research, even though you try to optimize your own career, of course, is a very collaborative effort, and you will need a network of collaborators in order to be successful. So you can write papers together, you can write grant proposals, you can write events, you can, if you leave academia, you need somebody who hires you that could be a former collaborator. You can exchange students and people afterwards once you're more senior. And also, it's much more fun if you visit a conference or workshop if you already know some people than if you don't. So it's never too early to start working on a network. So you can just turn left and right, exchange your contact details, and maybe 5 years from now, you're writing each other recommendation letters. So that's all from me. Thank you. Nobody turned left or right. I mean it. Connect, right? Exchange emails.
I will support this statement that actually at this point that when you go to conferences, you don't need to connect only to big professors.
No.
You connect to other PhD students, other postdocs at your own age, because 5-10 years fast forward, they are the big professors. So these relationships that you develop with the peers of your own age will take you much further long run.
I mean, what you very often see is that when some famous Turing Award winner enters the room at one of these conferences, it's not that there are so many, but that then all the students, assemble around them and say, oh, I always thought you're the best. I mean, that person doesn't care, right? They will not remember your face, right? Have a drink with somebody, your own age, or maybe a few years older. That helps because they are professor before you. So, but don't lick the boots of the Nobel Prize winners. Unless you know them personally, then they can write you letters.
Don't lick the boots, period.
Good point.
No more questions?
I have nothing else to do. Please.
Okay, let's thank Christoph again.